Phytosauria. So, you know who I am, and that's my title. So this is my PhD research into the functional and morphological similarity with phytosaurs and crocodilians. So phytosaurs in media in general, they get portrayed as like the big bad guys of the Triassic, and they're just portrayed as sort of going around munching and terrorizing the macrofauna, and just being general toothy terrors. But is this really fair? So phytosaurs don't actually have that many functional studies. And most of this reconstruction is based entirely on the fact that they are quite similar to crocodilians morphologically. They've got a full body convergence going on. So phytosaurs are restricted to the late Triassic. There is a phytosaur that's from the early Triassic, but it's dubious and we won't talk about it. And they've got quite a good global range all around at the time, well, when they were alive. So just to give you an idea of where exactly the phytosaurs sit, here is the Ichthyosaur tree, and for anybody who doesn't know, it's split into two main lineages. So you've got the Ornithodira lineage, which is containing the pterosaurs, and because everybody really likes to know where the dinosaurs are at all times. Here are the dinosaurs, and they end with the birds, so that's one of the crown groups of the Ichthyosaurs. And then on the other side, you've got the crocodilian stem. So you've got the Pseudosucha and all these disparate morphologies ending in the crocodilians. And phytosaurs are very much basal in this phylogeny, which is ripped from Martin's new paper. So let's have a look at the phytosaur general morphology and compare that to crocodilians. So we can see that there are some really robust forms right at the top there, both in crocodilians and phytosaurs. So the phytosaurs are on the left and crocodilians on the right. And you can see that there are also some really slender, sort of tube-like rostra going on as well in both groups. But then you see the similarities kind of end because you get these massive crests going on in some forms. And none of the excellent crocodilians have any of these kind of crests. You have the nares just before the orbits in phytosaurs, whereas the nares are restricted to the end of the rostrum in crocodilians. You get other crests. So like there's this crest going on and little crests on the premaxillary phytosaurs. And it gets even more disparate when you look at phytosaurs in dorsal view and compare them with crocodilians. Even the most robust phytosaurs at the top there, they have this morphology where their rostrum comes in very, very distinctly. And no crocodilians really do this. There are some that sort of do it, the more gracile forms do as well, but the more robust ones are very broad in general. So, before I go any further, I'll just explain what exactly I'm doing in my PhD. The first step is to produce a global phytosaurian phylogeny. So this maybe seems a bit random to do, but if I'm being really pretentious, I'll quote that. So, if you've got two groups and they look the same, then they might share morphology because they're very closely related, or they might share functional. So you can't really figure out which is which unless you've got a good phylogeny, or at least it's very difficult. So this is the reason I'm putting everything in context with a good phytosaur phylogeny, which really needs updating anyway. So next, I'll compare quantitatively shape variation between crocs and phytosaurs. That'll be geometric morphometrics, and doing some functional studies about the stress that could accumulate in the skulls of both groups and compare those. And finally, look at tooth microwear, trying to see what kind of materials the phytosaurs are going to eat and if they are similar to crocodilians. So today I'm just going to focus on these phytosaurs. And there is one main problem talking about the phytosaur phylogeny. There's one main problem with phytosaur phylogeny at the moment, and that's the Atlantic Ocean, which wasn't there in the Triassic and very much is now. So this is demonstrated by phylogeny by Stocker in 2012. So she's got loads and loads of species involved in this phylogeny, which is great, but they're pretty much all American species. And as you can see, there are species in America and in Europe and sort of various other places. And there's another study by Axel Hohenbuehler, who is based in Europe, and he's got a nicer spread of, like, there are some American, there are some European, but there aren't many taxa involved. So essentially what we have is poor sampling transatlantically. because it's kind of a lot of effort to go across the Atlantic, right? But it's also interesting to figure out, is there actually a genuine phylogenetic divide between these two continents? We can probably figure that out if we have a really good phylogeny. So my Cladistic analysis, I have 91 specimens, 13 institutions, 23 taxa, so already it's more taxonomy sampled than previous analyses. And there are 72 characters, and I did TNT analyses with various algorithms to try and search tree space fully, to try and resolve what's going on. So here's the tree. It's made up of 12 most parsimonious trees, so this is a majority consensus tree, and it's looking quite nice. And we can see where the various morphologies map on. So we get some more robust morphologies in the middle, and some slightly less robust morphologies at the edges, but realistically, these have sister taxa that are also gracile and robust, so it doesn't really matter. But what's interesting is that there's no real divide between the American and the European taxa. So it doesn't seem like there's really any reason, apart from just not having the resources to do so, for splitting apart the American and European taxa. So if we then do strict consensus, we have a massive polytope, which isn't great. So what can we do about this? This is one of the things that I have done is use a technique called iterative PCR, which is a reduced consensus method, and it applies to the analysis post hoc. So what it does, it has an algorithm that identifies and removes unstable taxa that are causing polytopies. These taxa are removed at the end, so the good thing about this is that those taxa are still contributing to the analysis. So even though they are removed afterwards, you still get them affecting other taxa's positions in the tree, but you just get better resolved results. So the tree that I get out from that is this. And again, yeah, it's better resolved, but it is missing some taxa. We can see what those taxa are now, and we can also see where they're plotted on the tree. So it gives you a good idea of what taxa you need to look at and maybe sample better. So that's something that I'll be going forward and doing in the future. So next, moving on to geometric morphometrics, which is the second part of my sort of PhD at the moment. So geometric morphometrics is shape analysis, as we've heard about before. And we need to figure out what exactly is shape, because it's kind of tricky to pin down. The best definition is whatever remains following the removal of size, location, and orientation. And a good example is this. So you can all see that it's the Eiffel Tower. It's not Blackpool. But it's quite a lot smaller than the Eiffel Tower, and it's on its side. Also, we're not in Paris. So what's going on here? How do we know that it's the Eiffel Tower? Well, we're looking at its shape. We're looking at various maybe points on it, certain bits where certain features maybe correspond. So that's what geometric morphometrics does with landmarks. So you plot landmarks, plot homologous positions within skulls, in my case particular in skulls, and then using covariation, we can take those points and covary them onto PC axes. So in this case, these PC axes may convey thickness, or for example, or gracility. And what we can do after that is plot over the top the phylogeny, so we can get a good idea of how a species is evolving in terms of its shape as it evolves as a species. We can also do this in 3D, so one of the things that I'm trying to do at the moment is gather together a photogrammetric data set of phytosaurs, so I'm going around taking loads of photos and creating 3D meshes. And the problem with this is that lots of phytosaurs are really deformed. So these are two species. These are two of the same species, rather. This is the holotype. It's really flat. And this is one from the NHM in London, and it's not flat. This one has a really nice posterior portion of the skull, and this not so much. Also, this has a big crack running down the middle. So what we can do, using a software called IDAV Landmark, is, first of all, retrodeform any breaks in the skull, any sort of deformations that are easy to sort out. And then, using landmarks, we plot a load of homologous landmarks from one skull onto the other. And we can warp one skull to the shape of the other. So, this skull in this case, it's been heightened to the shape of that skull. What that means we can do is take the posterior portion of the blue skull in this case and transfer it onto the orange skull, and we have a composite model of what this species would have looked like. So that, among various other techniques, is what I'm trying to do to deal with this deformation. And there it is in dorsal view. So I only use one half because it's bilaterally symmetrical. And some preliminary results, only in 2D, show, well, we've got along PC1 shape change in the slenderness of the rostrum. So here you've got really slender rostra, and here you've got much more robust. Down in PC2, we've got the elevation of the nares and general sort of height of the skull. So we can see that coming from the root, which is just up there, we have some quite basal taxa that are extending right out towards the edges, towards the really gracile sections, and others that are really becoming more robust. Coming towards the most derived part of the tree, sort of up here, we find that most of those are now more robust, but we do get some reversions to a more gracile, more basal looking shape. So, for example, these mysterious suture species are quite derived in the actual tree itself, but in terms of their morphology, they look very basal, really. So that's my preliminary results. I'd like to thank these people because they're nice and they help me. And any questions would be fine.